All right, so the past couple of days we've been talking about Vesper theory and the shapes of molecules, so we did that molecular modeling lab. A lot of people have been asking me, what do you need to memorize? You do need to memorize the individual shapes for molecules up to the tetrahedral electronic geometries. So for example, you need to know linear geometries, trigonal planar, bent, tetrahedral, trigonal pyramidal, and bent again. So I could give you a problem on an exam, ask you to draw the Lewis structure and then the overall 3D shape, and you unfortunately can't use a model kit on exams for this class. So one thing I would recommend is go back to that molecular model sheet and use this as kind of a rough guide and practice. There's a blank copy on the website, so you can print it off and see if you can solve this on your own at home, but it's a good way of reviewing. All right, we did end with one part on Wednesday where we were talking about polar versus nonpolar molecules. And let's take a look at these two on the bottom. So we said that carbon dioxide is nonpolar as a molecule, even though we have individual polar bonds in it. Why is that? Yeah, they cancel out, right? So if you've got individual polar bonds, but they're pulling in equal and opposite directions, they will cancel out. Where the one on the left, the OF2, in this case, they're not canceling out because both fluorines are pointed a little bit down. That means that there's a net dipole pointed down towards the fluorines. So that's a really important thing. But in order to predict whether or not a molecule has a net dipole, we need to know its overall shape. So let's make a couple of notes regarding that. So bonds can be polar if there is a difference in electronegativity, and molecules can have a net dipole if there is an overall imbalance of electron density. Okay, so that's a key thing. The big thing to watch out for is sometimes molecules have individual dipoles within their bonds, but they cancel out. Whoop. Okay, so let's do a practice one. I'll give you guys a molecular formula. First thing I want you to do is to draw the Lewis structure, meaning the 2D structure, and then determine its overall shape, and then decide whether or not the molecule has a net or overall dipole. So the first one I'm going to do is BF3. So let's try to draw the Lewis structure. And then we'll determine whether or not it has a net dipole. So what do you think the central atom is going to be? Probably the boron, right? Okay. How many valence electrons around boron? 3. Okay, so we've got 1, 2, 3. I'm going to switch colors for fluorine. So we've got 3 fluorines. How many valence electrons for fluorine? 7. Okay, so 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, we can match these guys up. We can match these guys up and these up. So I'm just going to redraw this down here a little bit differently, clean it up a bit. All right, now we need to determine its three-dimensional shape. So when I'm looking at boron, how many bonded atoms plus lone pairs do we have? Just 3. There are no lone pairs on boron, right? So what electronic geometry would it be? Yeah, trigonal planar. And then its overall shape would be what? Trigonal planar too. So sometimes you run into that situation where it matches. So in this case, we know that BF3, or boron trifluoride, would best be represented with those fluorines kind of evenly spaced away from one another according to VSEPR theory. And we know each of these angles is about 120 degrees. But they're all flat. So you could lay this down on a table and it'd be flat. You don't have to draw any dashes or wedges. Okay, so now if we look at this, do you think there's a net dipole? Why not? Yeah, they're all pulling in equal and opposite directions, right? So in this case, we would say that there's no net dipole. They cancel out. This is kind of confusing because there are some molecules that look really similar that do have net dipoles. And so let's take a look at another example. Let's do NF3. So same sort of thing, we'll do a Lewis structure. We'll do a 3D structure, and then we'll ask if there's a net dipole. So let's start with nitrogen. It's going to be our central atom again. How many valence electrons? 5. So 1, 2, 3, 4. 3, 4, 5. There we go. And I'll do fluorines again in red. We said that they have 7 valence electrons. Oops, that should be an F, not an N. Okay, so when we go to pair these up, compare up the unpaired electrons, you can redraw this as a cleaner Lewis structure. Remember with Lewis structures to include all of your lone pairs. The lone pairs are important. And now we have to determine its 3D shape. So first thing I do is I look at the nitrogen. I count the number of bonded atoms and lone pairs. In this case, we've got 4, right? 1 lone pair, 3 bonded atoms. That means this is a tetrahedral electronic geometry, but what's its overall shape? Trigonal what? Pyramidal. So this is one where it doesn't lay flat. It's not trigonal planar. It actually wants to adopt more of a pyramid type shape. And the reason it does this is that this lone pair occupies space, so we need to account for the space of the lone pair. So this is trigonal pyramidal. All right, so does this have a net dipole? Yeah, absolutely. If we look at it, all the fluorines are puckered down. That means the electron density is going to be pulled towards the fluorine. So this does have a net dipole. And if we were to draw the vector showing the direction of the dipole, I would show it going straight down, and we're pulling electron density away from the side of the molecule that has the lone pair. If we go back and we look at the one up here, we do have individual dipoles, but we said that they're all kind of pulling in equal and opposite directions, so they're canceling out. Where with this one, if we're looking at it, we've got one dipole this way, one dipole this way, one dipole this way, giving it an overall net dipole pointed down. Does that make sense? It's really important that you understand the shapes of molecules before you describe whether or not they have polarity. Okay, so now we get to go into kind of tedious stuff, but kind of interesting stuff. Naming. So I really like this article. I found it. It came out in 2004. So the city officials were so concerned about the potentially dangerous properties of dihydrogen monoxide, they considered banning foam cups after they learned the chemical was used in their production. Then they learned, to their chagrin, that dihydrogen monoxide, H2O for short, is a scientific term for water. It's embarrassing, they said. We had a paralegal who did bad research. This happens almost on a yearly basis, where somebody goes on the radio or says something publicly where they're like, if you inhale dihydrogen monoxide, you will suffocate and die. Don't let your kids get exposed to it. It's like, it's water. You're talking about drowning, of course. You don't want to inhale water. So we need to be really, really careful with how we name molecules. And so we're going to first start with naming covalent molecules, and then later on we'll talk about naming ionic compounds. But in order to name covalent molecules, we have to talk a little bit about prefixes. If you look here, they're using di and mono prefixes. What does di indicate? 2, and mono 1. So let's go through all the prefixes that are used in naming. So the first one we said is mono, and that indicates 1. Next one we've got is di. We said that's 2. What do you think the next one's going to be for 3? Tri. Not too bad. 4? Tetra, not quad. Oftentimes students will be tempted to say quad, but that's just not used in chemistry. Tetra is. What about 5? Penta. So you can think of a pentagon. What about 6? What do you call a 6-membered shape? It's a hexagon, right? So hexa is a prefix for 6. We'll go all the way to 10, 7, 8, 9, then 10, and then we'll cut it off at 10. What do you think 7 is? Close. It's actually hepta. What about 8? Octa. So like an octagon. All right, what about 9? Does anybody know that one? Nona. Which makes sense, right? So if we think about nano, the n is 10 to the 9th, right? So 9, known. Okay, 10 is deca. So not too bad, but I think it makes more sense when we use examples. So let's do this one. We got CO2. One thing I will say is I'm going to put an asterisk here. Don't use mono if it comes first. It's kind of implied. So for this example, CO2, what would we call this? Carbon dioxide. We wouldn't call it monocarbon dioxide, right? That sounds kind of funny. So don't use mono here. This would be carbon dioxide. And the di just means that we've got 2 oxygens, and we represent oxygen by calling it an oxide. Not too bad. Let's do another one. CO, a relative. Carbon monoxide. In this case, we do want to use mono because it's not going first. And this is what you typically have the detectors for in your house, is carbon monoxide. Does anybody know why? You can't smell it. You can suffocate without knowing. Essentially, it just makes you dizzy, you pass out, and then you die. It's a really interesting molecule. What ends up happening is it will bind to your blood at the same site where oxygen binds, and it won't let go. Meaning your blood gets completely taken over by carbon monoxide and it has no place left for oxygen. That's why it's really important to have these detectors in your house. All right, let's do a harder one. Let's do N2O4. What do you think this would be called? Okay, so dinitrogen. It's for 2 nitrogens. And then what would it be for the oxygen? Tetraoxide. And you may notice too that we're using these prefixes, and then typically the last part is going to have this IDE suffix too. So anytime you have a suffix, try to swap it over to IDE. Let's try another one. Let's do P4S3. What would this be called? Okay, so tetraphosphorus. And the S is sulfur, so this would be tri-sul. What would the suffix be? Sulfide, so trisulfide. Okay, so we've got our prefixes, and we've got our IDE suffix. That looks good to me. So tetraphosphorus trisulfide, not too bad. And then the example we saw in the paper was H2O. In this case, we're not saying mono first, so we do want to include it. So in the paper, this was dihydrogen monoxide. So if you want to sound sciencey around your friends, you can call it that instead of water. You're like, can you get me a glass of dihydrogen monoxide? Your parents might be irritated though. Okay, and then the last one we'll do for practice is SCl2. Okay, so sulfur, we don't use mono. Di, fluor, and then what goes last? Ide. Okay. So really naming covalent compounds is pretty straightforward. We will get into naming organic compounds later on in this term. However, for right now, try to use this naming convention as much as possible. It's really simple and easy. All right, so if we look at these, they're all covalent compounds. And how did we identify covalent compounds? They share electrons, right? Are they between metals or nonmetals, or a metal and a nonmetal? So if we look at like carbon dioxide and we go over to the periodic table, they're both on the right-hand side, so they're both nonmetals. Carbon monoxide, same thing. Nitrogen tetraoxide or dinitrogen tetraoxide, nitrogen and oxygen are both nonmetals. Same thing with phosphorus and sulfur. Basically, all of the covalent compounds that we're going to be looking at are between nonmetals, right? So then the question is, well, what if we have a metal in there? What would we do? And that leads us into our next section, where we talk about ionic bonds. So let me pull up another cheesy video.
Welcome.
Just a second, let me get this plugged in. Put the volume up. Where'd it go? Oh, no. This doesn't like my...
First lesson is chemical bonding. Chemical bonds are what holds atoms together. A chemical bond is an attraction between atoms that allows the formation of a chemical substance. The electrons that participate in a chemical bond are called valence electrons. These are electrons that are found in an atom's outermost shell. Let's take a look at the types of chemical bonds that can be formed between atoms. An ionic bond is formed will lose its electron to the other atom. This results in a positively charged ion, called a cation, and a negatively charged ion, called an anion. Positive and negative attract, and the result is an ionic bond. Covalent chemical bonds involve the sharing of a pair of valence electrons by two atoms. There is also what is called polar covalent bonds. These are covalent bonds in which the sharing of the electron pair is unequal. The result is a bond where the electron pair is displaced with the more electronegative atom. Thanks for watching. We'll see you guys next time.
Thanks for humoring my dog videos. All right, so a covalent bond, like the video said, it is where you share electrons. And this is usually between nonmetals. Let me slide this over a little bit. And then ionic bonds are a transfer of electrons. And this is usually, however not always, between a metal and a nonmetal. So the easiest way to identify a metal versus a nonmetal is to look at the side of the periodic table, right? So typically the left-hand side is going to be considered metallic, and then that top right-hand corner is going to be your nonmetal side, right? So everything in purple on here is considered nonmetals. Everything in orange, including that transition block that they cut out, can be considered a metal. And then with the metalloids, we're not really going to talk about those very much, but those do have some properties that are both metallic-like and covalent-like. All right, so let's take a look at a cool reaction here. So let's say we've got sodium, right? Sodium in this case has how many valence electrons? Just looking at the periodic table, it's in group 1, right? Where chlorine, on the other hand, has 7. And the octet rule basically says that atoms would prefer to have an octet of electrons, right? So if we look at this reaction, what's going to happen is sodium says, here, take this. And then when it goes over, sodium's now missing an electron, so what charge will it have? Positive. So I'll just put a plus in the corner. Chlorine over here gained an electron, and so what charge will it have? Negative. Really, all an ionic bond is an attraction between a positive and a negative charge. These reactions are actually pretty amazing to watch. So if you take elemental sodium and chlorine gas, you can actually see the reaction take place. And then what's NaCl? Does anybody know? Salt. It's just your standard table salt. So let's see if we can pull up this video. Come on. Let me pull it up in this notebook. Sorry, guys. I don't know why it won't open in that folder. So we'll take a look at what this reaction does.
On this sodium metal to activate, and you should see a pretty brilliant reaction once that activates. He's trying to drop some water with a
pipette and start the reaction.
There it is. And that white smoke you see is sodium chloride solid, colloid. That white smoke is the presence
Of sodium chloride that you made. And as it dissipates, we'll see where the sodium was, or the sodium metal was, is now going to be a crystal lattice
of sodium chloride. Notice the color of the flame was indicative of how sodium metal or sodium electrons get excited and, of course, emit energy.
So as this calms down, okay, we notice this is pretty thick smoke because this is essentially sodium chloride. So I can actually pour this out because it's solid. But what I want to do is I want to wait to see
What it looks like after it's done. When it's done, when all that sodium chloride dust settles, you should be able to see a crystal lattice.
Let's fast forward a little.
that's kind of milky white on the outside. That's where the sodium chloride dust has settled. But if you look very carefully, you'll see a white spot. That white spot, and I'll get a close-up in a second, represents where the sodium was in highest concentration, and that is where you see some solid sodium chloride crystals. So let's zoom in to some
Very close space, and you will see right there, as I focus, that is where the sodium chloride is in the places where the sodium metal was. So the sodium chloride, sodium plus.
All right, we'll stop it there. But the key takeaway from that is that anytime you do these transfer of electrons, it releases an incredible amount of energy. It's not a very practical way of making salt, though, obviously. Yep.
So, our eyes, like the chloride, we need gas.
The sodium chloride that he made?
No, for like clean eyes.
Any?
We need gas.
Sorry, say that again.
Like eyes, the separate eyes.
Oh, so the IDE suffix for naming is typically only used for the covalent compounds. We'll talk about ionic nomenclature soon. They have a completely different set of rules for naming ionic compounds. Yeah, that's a good question, though. Okay, so we said previously that sodium has this positive charge, chlorine has a negative charge. These are referred to as ions because you've got extra or not enough electrons. So ions are atoms or molecules with a charge. So we can break this down into cations and anions. Does anybody remember which one is which? Which one's the one that has the positive charge? Cation. And with anions, they are negatively charged. Oop. The way I always remember this is, let's highlight this. Cations has a T in it. I know this is kind of cheesy, but the T, I always imagine this as a positive sign. Other people will say, all right, that N in anions could stand for negative. However, there's an N in both of them. So I really like looking for the T. The T indicates that you've got that positive charge. It's a simple trick you can use. So let's take a look at a few of these. And we'll go back and review some. Let's do protons, neutrons, electrons. We'll do a charge. And then I'll put cation or anion. Okay, so let's do this first one real quick. So sodium, let me zoom in. How many protons does sodium have? 11, based on its atomic number. How many neutrons will it have? 12. How many electrons? 11 because there's no charge listed, so a charge we'll just put 0. And we'll put neither here. It can't be a cation or an anion as its neutral form. However, what if we take away an electron? And it still has 11 protons. That hasn't changed. It still has 12 neutrons. How many electrons now? 10. Which means it has a charge of +1, and it's going to be a cation. All right, and then we can do something like Cl- with 35. How many protons does chlorine normally have, or always have, I should say? 17. How many neutrons? 18. And electrons? 18. It's got 1 extra compared to the protons, so it's 18. This would have a charge of -1, and it would be an anion. So make sure that you're comfortable identifying an anion or a cation if I were to present one to you. All right, let's talk about the formula unit. So for covalent bonds, there is a fixed ratio of atoms. And the example that's really simple would be something like water. What's the formula unit for water? Or the molecular formula? H2O. So for every 2 hydrogens, we have 1 oxygen. We have a similar trend for things like anions too, and I'll show you how it differs. With covalent bonds, though, they're kind of stuck together. The hydrogen is floating or directly attached to the hydrogen, and you might have another water molecule floating nearby, so you've got these individual units taking up space. For ionic bonds, it's a little bit different. There's a fixed ratio, but there is a 3D lattice. And I'll show you guys what I mean by this lattice structure. So let's imagine we've got sodium positive and we've got chlorine negative, right? We can basically turn this into a wall where we've got sodium here, we've got chlorine here. They're attracted to one another because they've got opposite charges, right? And then we could alternate another sodium. We could have a sodium up here, kind of surround this chlorine atom with sodium cations. And then we could throw in some more chlorines, some more chlorines, some more chlorines, some more chlorines. And basically what you end up with is an infinite 3D lattice. And this isn't just one flat sheet. It actually forms more of a cubic shape because you can imagine this forming a cube, right? And there's an infinite 3D lattice, but still a 1-to-1 ratio of sodium cations to chlorine anions, and that's an important thing to remember. Why do you think there's a 1-to-1 ratio as opposed to a 2-to-1 ratio or any other ratio? Does anybody know? Yeah, absolutely. So if we look at this, ionic compounds want to cancel out each other's charges. That's one way of thinking about it is, so in order to cancel out that 1 plus, you have to have 1 minus, right? If you have a 2 plus cation, then you might need 2 negative ones to cancel it out. So that's how you determine the ratio. So it's a little bit weird to think about, but here's a better representation than my crummy drawings. So the cations are the sodium ones. They're shown in blue. Chlorine's negative, right? And we can form this big 3D lattice, but it's still a 1-to-1 ratio. You can expand this out bigger, bigger, bigger. And if you actually look at salt crystals under a microscope or using a good magnifying glass, you'll actually see the cubic structure of their lattice framework. But it's still just a 1-to-1 ratio overall. Does that make sense? Okay. So let's talk about how we can predict the charge for a cation or an anion, and it's pretty dang easy. So let's make a little note. Main group atoms will gain or lose electrons in order to have an octet. So if we look at the table, it's pretty straightforward, right? So if you're in group 1A, you lose 1 electron, that gives you an octet, that gives you a net positive charge. If you're in group 2A, you can lose 2 electrons and then have an octet, and that gives you a positive 2 charge. One thing I will say is these transition metals are kind of confusing. The charge can vary. So we're going to talk about transition metal complexes later, but for right now we're focused on the main group, so basically anything that's not in that center group. And then once we hop over to the other side, you'll notice that aluminum can lose 3 electrons to give an octet. And then over here we kind of switch over the other way where we say, all right, nitrogen and phosphorus can gain 3 electrons to get an octet. Oxygen and sulfur can gain 2 electrons to get an octet. And fluorine can get 1 electron to have an octet. So the easiest thing to do is to look at these and classify them. These are always going to be +1. These are always going to be +2. In group 3A, they're usually going to be +3. Group 5A is always going to be -3, and then -2, and then -1. All right, kind of an abstract question though. If we think about sodium, right? We said that it's pretty happy giving up this electron and then going to sodium positive. But why doesn't it take 7 electrons to form an octet? What do you think? Yeah, exactly. It's really the path of least resistance. It's easier to give up 1 electron than it is to find 7 electrons. So in this case, try to find the closest route to an octet. That's why over here we don't say it's got a +5 charge. That would take more work than gaining 3 electrons to get to that octet. All right. And then we'll do some practice and then hopefully get out of here a little early. So in order for an ionic compound to be neutral, your charges must cancel. Okay, so the example we saw was if you take sodium cations and chlorine anions and you put them together, they're already going to cancel each other out. You've got 1 positive, 1 negative, so it'd just be NaCl. You don't have to say Na1Cl1. It's implied that there's just 1. But let's do some trickier ones. Okay. What is the salt that forms meaning the ionic compound, when potassium reacts with oxygen. So I'll give you guys a minute to think about this, but what I normally like to do is draw the Lewis structure for the neutral atom and then figure out how it can get to a full octet. Does it want to steal electrons from another atom, or does it want to give them away? And then check with your neighbor and see if you guys agree. I'll give you a hint too. You can use more than one potassium atom or more than one oxygen atom. Your goal though is to balance out the charge. So I'll get us going really quick. How many valence electrons for potassium? 1. Pretty easy. All right, oxygen, how many valence? 6. 2, 3, 4, 5, 6. Okay, so looking at potassium, do you think it wants to steal 7 electrons or give away 1? Give away 1. That's pretty easy. Okay, so it'll probably give it up to this oxygen. Makes sense? All right, so if we do that though, oxygen still doesn't have an octet. What's the solution? Another potassium, right? Okay, so if we take this one, we can say, all right, we'll donate it to this side. Which makes sense because now we'll have 2 potassium cations. We know that group 1A elements like to form +1 charges. And then oxygen over here now has a full octet of electrons, giving it what charge? 2 negative. Okay, so if we were to write this out as a formula unit, you usually want to list your cation first, followed by your anion. So this would just be K2O. Not too bad. All right, let's do another one. What salt forms when magnesium reacts with nitrogen? So this one's a little bit trickier. And then check with your neighbor and see if you agree. Yep.
With the K2O, if it wasn't balanced, would you write negative?
Yeah, for a non-neutral compound, you might have a charge, but we'll talk about that a little bit later. For right now, we're going to focus on trying to make neutral salts. Yeah. Okay, so magnesium has how many valence electrons? 2. It's in group 2A. I'll say 1, 2. Nitrogen has how many? 5. So I'll say 1, 2, 3, 4, 5. Okay. So if we look at magnesium, would it be easier to steal 6 or lose 2? Lose 2. Okay, so I'll say, okay, I'll give 1 to that side. I'll give 1 to this side, but the nitrogen still doesn't have an octet. Simple solution is add in more magnesium, right? Okay, so then I'll say magnesium right here and here. Okay. It'll give it that 3rd electron that the nitrogen wants, but now it's got an extra electron. What's the solution? Okay, so maybe add in more nitrogen and maybe more magnesium if needed in the end. So let's try that. Okay, so that electron on magnesium has to have a home. So I'll give it to a 2nd nitrogen, but now this nitrogen needs 2 more electrons, so maybe we need 1 more magnesium atom. Okay, so now the magnesiums have all lost their electrons. They're happy with an octet. And the nitrogens have each gained 3 electrons, which gives them an octet. So if we look at this, we've got 3 magnesium, 2 pluses. And we've got 2 nitrogens, each with an octet. And what was the charge on the nitrogen? 3 negative. So the formula unit for this would be Mg2 as a subscript, and then, Mg3, and then N2. Pretty straightforward. I'll show you guys a simple trick though. Sometimes this gets overwhelming when you're first learning it. So what I do is I look at my cation that has some sort of charge. I'll call this plus X. And my anion that has some sort of charge of negative Y. And I'm going to take this charge and move it to be a subscript for the cation. And I'll take this charge and move it to be a subscript for the anion. So the example we had just covered was with magnesium. And we said magnesium, because it's in group 2A, always has a charge of positive 2. Nitrogen, because it's in group 5A, always has a charge of negative 3. I'm going to take this 3, scoot it down here, and this 2, scoot it down here, which means that we're forming Mg3 and 2. That way you don't have to go through the hassle of drawing out all of your individual atoms. Does that make sense? All right, I think that's where we're going to stop today. When we come back on Monday, we'll talk about how to name ionic compounds, and I would encourage you guys to get started on sapling over the weekend. If you guys ever run into questions on sapling, don't hesitate to email me. I'm more than happy to help you guys out, and I want to know where you guys are struggling.